Today we're going to look at just some basic background as to the structure of the atom. Hopefully most of it is going to be review for you. You're likely familiar that there's three types of particles in an atom. There's a central core to the atom, which we call the nucleus, and inside that central core there's going to be some neutrons and some protons. And we have a collective name for those particles found within the nucleus. So if it's a neutron or a proton, we can give it the collective name and call it a nucleon. Something that's found, a particle that's found within a nucleus. Outside of the nucleus is where the electrons hang out. And they'll move around in orbits about that central nucleus. Or at least in our simplified Bohr-Rutherford model of the atom, that's what the electrons do. A few other basic facts. The mass of a proton is approximately equal to the mass of a neutron. In other words, all the nucleons have about the same mass. But that nucleon mass is much bigger than the electron mass by about 2,000 times, 3 orders of magnitude larger. And finally, we call the neutrons neutrons because they have no charge. The protons have a positive charge, whereas the electrons have a negative charge. And the magnitudes of those two charges is the same. So the magnitude of the charge of a proton is equal to the charge of an electron. It turns out the value of that charge is 1.6 times 10 to the negative 19 coulombs. We refer to that as the elementary charge. So in a neutral atom, the number of electrons is equal to the number of protons. And as a general rule, the number of neutrons is similar to the number of protons. We'll go into that in more detail. But generally the number of neutrons is the same as or a little bit bigger than the number of protons. The next important idea that you need to know about atoms is that the electrons, or the atoms as a whole, they exist in these discrete energy levels. So let's take a look at the very simplest of all the atoms, the hydrogen atom. It's simply a proton with an electron orbiting about it. Now, of course, we've got two charges interacting, and that means there's going to be some energy. There's going to be electric potential energy, which for 2 point charges that are oppositely charged and attracting each other and trapping one another is going to be negative Coulomb's constant times the product of the charges, but they both have that elementary charge, and divided by the distance of separation, which is simply going to be the radius of the atom. There's also going to be some kinetic energy because the electron's got some speed as it orbits around that central nucleus, and that would be given by a half mv squared. And normally when we add those two up, if I add up electric potential energy, a negative number, plus the kinetic energy, I usually get this number, negative 13.6 electron volts. So that negative 13.6 is called the ground state energy. It's negative because we'd have to add energy in order to free the electron from the proton. And therefore it's also called the ionization energy. Which is to say, if we add 13.6 electron volts of energy to a hydrogen atom, we'll knock the electron out of the atom, and the electron and the proton will be free of each other. We will have created ions. But what's unusual is, let's say that we add little energy. Well, the atom itself won't absorb it, won't accept any old energy. You've got to give it enough energy in order to get it up to the next energy level. Turns out the next energy level is negative 3.4 electron volts. So if you try to just add, say, 1 electron volt to excite the atom, nothing's going to happen. The atom won't accept that energy. So you must add at least 13.6 minus 3.4, or 10.2 electron volts. You have to add at least 10.2 electron volts to excite the atom and get it into a higher energy state. In fact, for a hydrogen atom, the energy levels look like this. In the first energy level, n equals 1, also called the ground state, the energy is negative 13.6 eVs. For n equals 2, as we said, it's equal to negative 3.4 electron volts. For n equals 3, we get negative 1.51 eVs. And for n equals 4, we get negative 0.85 electron volts. So you can see that the gaps in energy get smaller and smaller. The energy levels get closer and closer together as you go towards higher numbers of n. So if we want to excite a hydrogen atom, we can give it this much energy, that energy difference. Or we can give it this much energy. Or we can give it this much energy. If our atom's in the ground state, it can only absorb amounts of energy that will boost the atom into one of these discrete excited states. It can't accept just any old amount of energy. Now it turns out if we take our atom and we get it into an excited state, it doesn't stay in that excited state. It will fall back to the ground state. So if we go back to our hydrogen atom, there's our proton, and this can be our first energy level, E1. And let's suppose that we banged our atom, we gave it a little bit of extra energy, and the electron went to that second energy level and was hanging around in that second energy level for a little while. Well, it'll be a very short amount of time before it falls back to the ground state. And when it falls back to the ground state, something called a photon is emitted. So we're conserving energy here. That energy that we input comes out as photon energy. And what is a photon? It's the tiniest possible bundle of energy of electromagnetic radiation. You might hear it being called a quanta, or you might hear it called a particle of electromagnetic radiation. Now, so far we've talked about electromagnetic radiation being waves, but it turns out it has a particle nature as well. And this particle nature is represented by the photon. And the energy of the photon is proportional to the frequency of the electromagnetic radiation. If it's a very high frequency electromagnetic radiation, like say X-rays, then the photons, the tiniest bundles of energy, will be more energetic. If the electromagnetic radiation should be visible light, then the photons will be less energetic. And we can calculate the energy of the photon if we take a constant called Planck's constant and multiply it by the frequency. So this proportionality constant here is called Planck's constant, and it's given by this number, 6.63 times 10 to the minus 34. That would be joule seconds. And the F here is the frequency of the radiation. So if I have a big energy gap here, I'll get more energetic photons. I'll get radiation of a higher frequency. if the electron just has a little drop between energy levels, we'll get a less energetic photon and we'll get radiation produced that's of a lower frequency. Now when I was doing my diagrams of the Bohr atom and I was doing drawings like this, I'd say that there was, say, 2 neutrons and 2 protons and maybe 2 electrons out here. And that was my drawing for the atom. That was totally not to scale. Here's a drawing that's a little bit more to scale. The nucleus here is typically about 10 to the minus 15 meters. An atom has a size of about 10 to the minus 10 meters. So you're talking 5 orders of magnitude difference in size between the diameter of a nucleus compared to the diameter of an atom. So that's 5 orders of magnitude. So for instance, there'd be 5 orders of magnitude difference in size between a marble compared to a football stadium. So an atom is mostly empty space. And you'll recall that the mass of a nucleon, the stuff inside the nucleus, is about equal to 2,000 times the mass of an electron. In other words, pretty much all the mass of the atom is here, inside that tiny little speck of the nucleus. So in other words, a nucleus is really, really dense and really, really tiny. Now, how did we come to know that the nucleus is tiny, tiny and dense, dense? Well, it comes back to a very famous experiment. It is often called the Rutherford experiment. The IB would prefer that you call it the Geiger Marsden experiment, because Geiger and Marsden were the 2 guys that thought up this experiment and carried it out. Rutherford was just their supervisor. Simple experiment. Some alpha particles are fired at a very thin gold foil. Gold is chosen because it's very, very malleable, and you can get a foil of gold that's only a few atomic layers thick. Alpha particles are helium nuclei. So an alpha particle is a helium nuclei, so it's got 2 protons and it's got 2 neutrons, but it doesn't have any electrons on it, so it's going to have a charge of +2. So what happened in the experiment is that a photographic film was placed around the gold foil. And every time an alpha particle hit that photographic film, a mark would be shown. So Geiger and Marsden could find out where all the alpha particles were scattering after they hit the gold foil. So because we know where all these alpha particles deflect in the experiment, we get a good picture as to what the structure of the gold atom is like. So for instance, let's suppose we thought the structure of the gold atom was just a ball with a consistent mass throughout. And just to simplify things, I'm going to make our gold foil just 1 atomic layer thick. So there's our gold foil, but we've got a consistent mass throughout each atom. And we'd have the positive charge distributed consistently through the gold atom. So now if we send in our alpha particles, and the alpha particles have a mass that's about 1/50th the mass of a gold atom, these alpha particles would come in, and if our layer of gold atoms here was very strong, those alpha particles could bounce back. But we're not expecting that. We're expecting a single layer of gold atoms not to be held together very strongly, and that these alpha particles are just going to kind of rip through the gold foil like it was tissue paper. All of the alpha particles should just rip through. Now we get a very different prediction if we consider a gold atom to have a tiny, dense nucleus. So I'll do my single layer of gold atoms, but now I've got these tiny nuclei, and we'd have the electrons moving around the outside, creating the size of the atom. So here's my alpha particles. Typically, they're just going to pass right through because the atom's mostly empty space in this case. And the electrons are way, way too light to stop an alpha particle. So once again, most of the alpha particles would pass straight through. However, let's say we got a alpha particle coming and it came quite close to that nucleus. Then of course the nucleus is positively charged, the alpha particle is positively charged. You're going to get some repulsion and you're going to see some of the alpha particles have a slight deflection. If we got even closer, we'd get a greater deflection, maybe something like this. And there'd even be a possibility of an alpha particle hitting straight on to that nucleus. And remember, the nucleus is 50 times more massive than the alpha particle. So it's going to stay fixed and the alpha particle will bounce back. So you've even got a possibility that the alpha particles would come in and bounce straight back. And they could analyze that scattering pattern and make a pretty good estimate as to how big a gold nucleus had to be. And when they looked at that scattering pattern, it did not look like this. It looked more like this. So they knew the gold atom had to have a very dense, very tiny, positively charged nucleus. It's very important in this section on nuclear physics to keep these words, neutron, nucleus, nuclei, nucleon, nuclide, keep them straight, keep them distinguished. They have very different meanings, and in fact I find it really hard to give a lesson on nuclear physics because often the wrong word will pop into my head because the words are so similar. So keep these words straight. A neutron is a non-charged particle with mass about equal to the mass of a proton. It's also going to be about 2,000 times more massive than an electron. Nucleus, that's simply the central core of an atom. Nuclei is the plural of nucleus. So we don't say nucleuses, we say nuclei. A nucleon is one of two particles found within the nucleus. That means it's either going to be a neutron or a proton. It's a group name for neutron or proton. And then a nuclide is a unique nucleus. So we might say things like helium-5. That would be a nuclide. It's a unique nucleus. The 5 here means there's 5 nucleons. And we'd call that the mass number, because it's the number of nucleons that gives it mass. And then the fact that it's helium means that you have 2 protons. All heliums have 2 protons. And we'd speak of that number, 2 protons, as being the charge number or the atomic number. So as soon as we specify the mass number and the atomic number, then we've specified a nuclide. So we'd speak of hydrogen 1, hydrogen 2, and hydrogen 3 as being different nuclides. They turn out also to be different isotopes, and that's what we're about to talk about now. An isotope is a nuclide with the same number of protons. And when it's got the same number of protons, that means it's the same element, but a different number of neutrons. So they have a different mass number. And they're going to be alike. They're going to be the same in the sense that they have the same chemical properties. So they behave in the same way when they interact with other atoms. They're different in 2 ways. The obvious one, they're different in mass. And the less obvious one, they're different in terms of their lifetime and their stability. So for example, there are 3 common isotopes of hydrogen. Hydrogen 1, hydrogen 2, and hydrogen 3. And notice there, when we're naming these isotopes, we state the element, and then we state the mass number. that identifies the isotope uniquely. And of course, tritium here, hydrogen 3, is going to be more massive than hydrogen 1 or hydrogen 2. So they differ in their mass. They also differ in their stability. Hydrogen 1, regular hydrogen, and deuterium are completely stable. They don't decay. But tritium here has a lifetime of about 12 years. And there's also some other isotopes of hydrogen that we usually don't hear about much, but there is a hydrogen 4, and a hydrogen 5, and a hydrogen 6, and a hydrogen 7. We don't hear about them often because they have very short lifetimes. They're radioactive. And in this case, they happen to be synthetic, so they have to be made in the laboratory. They won't occur on their own. Let's review with a few IB questions. Pause the video, try the question, come back for the answer. So we've got boron 11 here. And that number 5 there, that's the number of protons, the charge number or the atomic number. So our correct answer has to be A or B. This number on top, the mass number, is the number of protons plus the number of neutrons. So if we take that 11, the number of nucleons, subtract off those nucleons that happen to be protons, we're going to be left with this number of neutrons. So the correct answer here is going to be A. There's 5 protons and 6 neutrons. Okay, pause the video, try the question, come back for the answer. First thing we know, number of protons has to be 29. So it's got to be one of those 3 answers. Second thing, the number of neutrons has to be 65 minus 29, which is going to be 36. So the answer has to be either A or D. Now, if we've got a neutral atom, that means the number of protons is equal to the number of electrons. And that means A here is wrong. If we're going to have a neutral atom, the answer has to be D. Okay, pause the video, try the question, come back for the answer. Which of the following provides evidence for the existence of neutrons? Well, it's not the Geiger Marsden experiment. The Geiger Marsden experiment showed that we have a very tiny, dense nucleus. It's really isotopes that tells us that we have neutrons, because we get these nuclides with the same chemical and physical properties, but they have different masses. So the correct answer here is B. Okay, pause the video, try the question, come back for the answer. So let's look at the alpha particle at a couple positions here. We'll take it right here where it's as close as possible to the nucleus, and maybe back here where it's a little farther away. There'll be a force of repulsion between those 2 positive charges, and it's got to be right along the line connecting the centers of the 2 charges. So we're going to have a repulsive force, and it's going to be quite strong when the alpha particle's here because the 2 charges are close together. And it's going to be weaker here because the 2 charges are farther apart. So which of these answers is correct? The force acting on it changes direction. Well, that is correct. And if you look through the others, you'll see that they're all incorrect. So the correct answer here is A. One final review question. Pause the video, try the question, come back for the answer. So we've got 3 isotopes. They're all silver, and what that really means is they all have the same number of protons, the same atomic number. So they're going to have the same physical and chemical properties. The correct answer is D. So summarizing, an atom has a central core called a nucleus. Inside that we find the nucleons. There's 2 types of nucleons. There are the protons and the neutrons. Outside of the nucleus, that's where the electrons are. And they're generally in their ground state, but if you give the atom a little bit of energy, they can go up into discrete energy levels. This nucleus here, it's very tiny and it's very dense. And we know that from the Geiger Marsden experiment. That's what gave us evidence. This particular nuclide is the nuclide boron 11, and we could write that as B511. This number on the bottom is the atomic number of protons, or the charge number. This number on the top is the mass number, or the number of nucleons. And there would also be other isotopes of boron. There might be a boron 12, It would have the same chemical and physical properties, but it'd be more massive and likely won't be stable the way that boron 11 is. And that's all for today, folks. Thank you very much.